Right, so thank you everyone for coming. This week, Thomas will tell us about constraints on contact type hypersurfaces in symplectic 4-Manifolds.
Oh, thanks a lot. It's a pleasure to be here. So everything that's new result in here is joined with Bulent Tosun. And so I guess Bulent maybe has also given a couple of seminars about some of this stuff, or at least related. So I hope I don't end up repeating too much, but maybe it's okay. That happens. I guess we'll see. But it's okay. So the title was about contact type hypersurfaces. So maybe I'll quickly remind you what that means. So if you have a symplectic manifold, maybe could be general dimension for the moment, and you have a codimension 1 smooth submanifold. This contact type condition means the following. There should be a vector field, say defined in some neighborhood of your submanifold, which should satisfy, I guess, a couple of properties. So it should be a Lugol field. So expands the symplectic form, or I guess that amounts to saying that something is closed, that you have either of those, okay, and then it should be transverse to the submanifold everywhere. Okay, so I mean, the picture that we're going to generally have is that Y will be a separating hypersurface. So you have something like this, and there's this vector field pointing from one side to the other. That guy. And in that case, so if you have this situation, so if you have a smooth domain in your manifold, with contact type boundary, that's what I'm going to mean by saying that W is symplectically convex. Okay, and so the basic question I wanted to try to explore a little bit is, if you're given this ambient symplectic manifold, what contact type hypersurfaces can you find in X? And well, what I'm particularly interested in is just the diffeomorphism type of the manifold, the submanifold. So what diffeomorphism types of codimension 1 submanifold Y are realized as contact type hypersurfaces? Okay. So maybe, I mean, this question is sort of overly broad, maybe, but before I sort of narrow things down, even, I'll just kind of point out that, I mean, when you have a contact type thing like this, this condition, these two conditions automatically tell you that when you contract the symplectic form with this vector field and restrict the resulting one form to y, that's a contact form. And so that, and the corresponding contact structure is independent of the choice of the Lua field. So contact structure. But I'm not assuming that this is given ahead of time. So I'm not fixing the contact structure on Y. So if you put it in there into X as a contact type hypersurface, a contact structure arises, but I'm not fixing it ahead of time. And it's probably, well, me being a low-dimensional topologist, I sort of said that we're in a 2n manifold, but basically for the rest of the talk, I'm going to focus on 4 manifolds with 3-dimensional submanifolds. Okay, so how can you find such things? Well, one place that you find symplectic convexity would be from complex geometry, in particular Stein domains. So what's a Stein manifold? Is well, there are lots of definitions, but one is that the complex manifold, which I think of it as the W, but anyway, W with an integrable complex structure J, that admits, say, a J convex Morse function. So some sort of exhausting, what some people call a defining. So maybe it should be bounded below. And in that case, so I'm not going to really tell you what J convex means. It's not super important for our purposes, but this condition means that if you take you can turn this function into a 2 form, so omega sub phi, which basically some sort of complex-like version of a Gaussian or something. This is the exterior derivative sort of composed with the complex structure J, and then there's the ordinary exterior derivative. Anyway, this form, the J convexity, tells you that this form is a symplectic form. Moreover, just stay here in the middle. So then you've got a complex structure in a symplectic form. You can turn that into a sort of associated metric, a Riemannian metric, and then take the gradient. That guy becomes a Lua field. And so that says that if you look at, say, regular sub-level sets, see maybe so. These guys become symplectically convex. In fact, this definition only really wanted the Lua field defined near the boundary, whereas here it's defined everywhere. But anyway, so you imagine some picture like this where you have W is sort of interior, W is the sublevel set of the Morse function, and then the gradient sort of points outward. Okay, so that's an example of a symplectically convex manifold or object or something. But the problem is for our purposes, we're supposed to be finding this inside of a given symplectic manifold X. So, you know, in the simplest case, you could look at X being like complex Euclidean space, like C2 or something. And the problem is that X is sort of seemed to be given ahead of time some symplectic structure. And this construction sort of is internal to W in some sense. It depends only on the complex structure. And that's sort of a different thing. In other words, this, even if you're sitting inside of an X, maybe it's a Kähler manifold, so you have a complex structure around, that omega sub phi doesn't have to have anything to do with the omega that was given to you on X to begin with. So even though it's sort of abstractly symplectically convex, it's not necessarily symplectically convex inside this given X. Does that make sense? So I'll just say some words. However, if you're say, maybe just to be concrete, you've got a Kähler surface, maybe X, omega X and J. Then it makes sense to talk about a Stein domain sitting in it. Then what I was saying was that omega phi and omega X need not agree. And so that means that omega isn't necessarily symplectically convex in X. Okay. So I guess maybe what I'll do is state a theorem, which is a combination of sort of several people's contributions that sort of indicate what you might, how you might think about this situation. So let's focus on actually this maybe the simplest possible case where X is C2, just the complex. This leads to call it the complex plane, right? It's a two-dimensional complex thing. So what its standard structure is. I don't know, maybe standard Kähler form, standard complex structure. And let's suppose you have a domain sitting in it, so like that picture. Maybe just a smooth domain to begin with. So domain, I guess, means for me, probably have talking about closures of domains or something, but you know, closures of connected open sets with smooth boundary, and implicitly, I'll probably take the boundary to be connected also. So really, just like that picture. Then, well, you can ask, you know, you've got the complex structure in C2. You could forget about the symplectic form temporarily. The Stein condition is strictly a complex condition. So you ask when this W is a Stein manifold. And since I'm a topologist, I sort of care about that up to isotopy. So I guess the first condition is that W is going to be isotopic to a Stein domain. C2. If and only if the sort of obvious necessary homotopical condition is satisfied. So I mean, W has to sort of so you take the standard complex structure restricted to W, that guy should be homotopic through almost complex structures.
your Stein structure on the
So in other words, W sort of has to admit a Stein structure as an abstract manifold. And if you want to deform this smooth embedding to get you to sort of realize it as a Stein submanifold of C2, then it's sort of clear that the condition would have to be satisfied. Thank you. And it turns out that's enough. So this is basically a result of GOMP. And GOMP doesn't care that it's C2. We could have done this sort of anywhere. Okay, so that's sort of part one of the theorem. So, but as I said, that's sort of not enough for us. So supposing you can do this, if you have such a Stein domain, so the Stein domain W, that's going to be isotopic, let's say Stein isotopic. To a symplectically convex domain. If and only if this, well, I guess strictly that the choice of this phi isn't determined by W, so I'm going to refer, so I suppose in principle there could be various different forms that sort of come from that, but anyway, one of them should extend as a symplectic form all of C2. It should be standard at infinity. Okay, so then, so what that would tell you is that somehow you've got this omega phi here, and then you sort of extend it out. Maybe it turns out that that two form extends to the rest of C2 as some omega, twiddle, whatever. But then, standard at infinity means outside some ball. It actually agrees with the standard one. And then there's sort of, I suppose, classical, well-known results that if you're on C2, symplectic form standard at infinity is actually equivalent to the standard one everywhere, and then you can deform this to become symplectically convex. So this is, I guess this is can be attributed to Schielebeck and Elias.
So an example for this setting is, for example, if I have a star-shaped domain, then I could take the phi to be like the semi-norm associated to it, like the two homogeneous or one homogeneous, some homogeneous extent, like function. Yeah. So set is.
I think so. Yeah. I mean, I think if it's, yeah. I mean, you're talking about something more sort of refined and detailed than what I have in mind, which is just that, this most obvious example is just the 4-ball unit ball. It's,
Yeah, I'm just trying to figure out
to
like
do any more.
what's deformations of the form. I mean, not any topological ball would be okay for you, right?
I think it would.
It would be
I think
okay.
it would. The thing is that the ball has only one Stein structure. And so if you realize that, star-shaped domain is some Stein domain in there, it's still Stein equivalent to the round ball. Unless I'm screwing something up, I think this is the case. And so then abstractly, you have to be able to Stein deform it to a round ball.
What is standard at infinity?
Standard at infinity means that it's symplectic outside of a large ball. It agrees with the usual form. Okay, and actually there's one more condition here, which I can just squeeze it at the bottom. So the third step is that this situation, so the second one, situation 2, that happens if and only if W is Stein as a topic to something called a rationally convex domain, which I'll define for you in a moment. In C2, this is a condition that was captured by Nemrowski. But in some sense, from the way I've written this theorem, you can think of rationally convex morally as like a combination of being Stein and symplectically convex. So, strictly speaking, you sort of have to do Stein first, then arrange for symplectic convexity, and if that's possible, that's what it means to be rationally convex. But intuitively, you think rationally convex basically means sort of Stein and symplectically convex. Okay, so but what is rationally convex really? So I wanted to mention this definition because we'll see it again in a more general context. So the condition is there again. There are various definitions, but the one of the equivalent definitions is that every point in the complement P, there's an algebraic curve passing through that point and missing your domain. So for all P, P2 minus W, there's an algebraic curve. Also the complement containing P.
This is any genus or?
Yeah, that's the only condition, just an algebraic curve. So you can phrase this in terms of function theory if you want. You kind of sort of that the family of rational functions, like this is sort of this domain should be convex with respect to them. So in the sense that like any for any point in the complement, there's a rational function whose like form is bigger on that point than it is anywhere here. It's kind of you can phrase it that way as well. Okay. So maybe one thing that's worth saying is that if you are in higher dimensions, n is bigger than 2, then it's a work of Eliasberg and Schulbach. That the conditions, the first 2 conditions there are actually equivalent. Well, and therefore 3, because 3 doesn't really say anything. I mean, 3 is true in general. Also, this sort of extension criterion for rational convexity is what Nemrowski did, but doesn't depend on the dimensions. So I guess yeah, 3 are equivalent. See, yeah. So there's sort of no distinction between rational convexity or between, or once you're Stein, then you automatically can become symplectically convex. And so, for example, that gives you loads of examples of contact type hypersurfaces in Cn as the boundaries of these rationally convex domains. But there are very few such examples in C2. So there's many contact type Y's at Cn, but very few examples known. Well, basically, because of a lack of examples, people have been a conjecture that maybe if you have a three manifold with the rational homology of a three sphere, first embedding number 0, and it should be contact type in C2, and the only such thing is the three sphere. But as far as I know, there hasn't been really sort of systematic studies that very much anyway. But just again about the diffeomorphism type of contact type hypersurfaces. So here's the theorem. Sort of the lead off, I guess, which is that Brieskorn homology sphere. This one. 22 or something. I'll tell you what these are roughly. Generally, these are three-dimensional manifolds. Smooth manifolds admits an orientation preserving embedding. I could just say R4 standard symplectic structure. It's a contact type hypersurface. Well, unless you include the three sphere as a Brieskorn sphere. So the goal for the remainder of the time here is I'm going to say a little bit about what goes into the proof. But really, I wanted to try to get towards more recent progress to try to think about embeddings in closed form manifolds. Questions? Aside from what a Brieskorn sphere is, if that's a question. So really, I guess I'm really going to tell you hardly anything about the proof. I just wanted to tell you enough about the tools that I have something to refer to later. So what's a Brieskorn sphere? It's a link of a certain normal surface singularity. So I'll give you sort of explicit definition for the simplest case. Simplest non-trivial case. So you take a link, by which I mean intersect with the sphere of a certain algebraic singularity. So you think these are three complex variables. So you're sitting in C3. So I've written down some hypersurface, which has an isolated singularity at the origin, and I take its link. So I do this. So here I am at S5. This surface is codimension 2. So you get a real codimension 2. So you have a three manifold sitting in S5, sitting there. That's so this is the hypersurface case. There's a similar definition for kind of somebody with more parameters. So the P, Q, and R are telling you these exponents. If you have a family of exponents like this, then you end up writing a system of like, n-2 equations like this in C to the n. And so it becomes a complete intersection singularity instead of a hypersurface. I didn't write everything down, but the point is that it's still a three manifold. And again, we're considering it just as a smooth manifold. It does sort of come with a natural contact structure, sort of almost from this definition, but I'm not taking that to be fixed ahead of time. So this is, I suppose this definition more or less makes sense for any PQ and R, but the homology sphere condition is that these integer parameters should be pairwise relatively prime.
I have a basic question.
Mhm.
So if you take the higher dimensional analog and you restrict it to a subspace of CN, like a C2 inside CN, do you get a Brieskorn sphere, like a three-dimensional Brieskorn sphere from the intersection?
Higher dimensional analog in the sense of like you,
Like
Write
take
down
X1 to Xn, like you said.
a hypersurface like this and then restrict to where like the last 5 of the variables are
Yeah.
0. I think then sounds like, if I'm understanding, that you would just get this again.
The original, like the three-dimensional one, yeah. Right, it just gives you the lower dimensional ones, like they are nested, that's what I'm trying to.
Yes.
Okay.
Yeah.
Right.
So here's a nice family of 3 manifolds. And would have kind of a lot of interesting geometry and topology that people like to study. One sort of obvious thing about, as far as this question, is that it's not entirely clear that a Brieskorn sphere can even be smoothly embedded into R4. And so maybe the theorem is vacuous, because none of them sit in R4 anyway. But it turns out that many, at least these 3 parameter guys, at least many such. Well, let's say it this way, many of these don't embed in R4 even smoothly. But lots of them do. And it's actually not known entirely which ones do and which ones don't. So there are plenty for which it's not understood. So the smooth embedding question is sort of open in that sense, but this is giving a uniform answer for this symplectically convex version of it. Okay, so the way the proof goes is to cook up an obstruction to a symplectically convex embedding or a convex type embedding, coming from what we used was Heegaard Floer theory. So just in a nutshell, what this does is that if you have a 3 manifold and it assigns to you a module, let's say FU module, it's written as HF plus of Y, so by F I mean a field with 2 elements. And it turns out it also assigns, if you have a contact structure, an element, usually written C is sort of a characteristic class living in this Floer group. Technically, it's sort of more like a cohomology class, so you can end up in the manifold with the opposite orientation. It's super important. The only thing that's particularly relevant for us right now about this element is that this is non-zero if C is fillable contact structure. Okay, then so the obstruction that is used to produce this theorem, I need to tell you one more thing about sort of the way the structure of this module looks, which is the following. This sort of a general structure. Implicitly, I guess to be kind of precise, let's just take Y to be a homology sphere. So the structure theorem makes it a little more complicated if it's not, but I want to get into it. So it turns out that this always has sort of a standard piece, which looks like the following module. Take that guy, sort of you take f of u and you localize it and then you divide by the, okay, that's just sort of what it looks like. And then there's some other piece called the reduced part. Another way to understand what these pieces look like, so that this part is sort of finite dimensional over f. And it's sort of, well, U torsion, I guess. This guy could also be described as the image of u to the n for any sufficiently large n. So maybe the more canonical definition of this piece is that it's equal to hf plus modulo of this image. So part of the structure is, of course, that this image stabilizes for large n. Okay, so what's relevant for our obstruction is you take this element here and you look at its image in this quotient. So, I mean, if you know something of Heegaard Floer, this isn't really super deep. If you don't, well, it just kind of, here's this invariant, lives in some group associated to the 3-manifold. And the obstruction is that essentially that product has to vanish if you're going to be a contact type hypersurface in R4. So maybe I'll number the theorems starting from here, at least some of them. So if y is symplectically convex, and R for standard symplectic structure, and C is the associated contact structure, then this reduced contact invariant thing has to vanish. And I can actually give you a little bit of the idea of why this happens. So, because again, it'll be sort of useful later. So here you have your symplectically convex domain. So it's got its boundary Y and its Liouville field pointing out. Let's just enclose this in a large ball. So this is Y and this is S3. And of course, the ball is symplectically convex. There's like a radial Liouville field transverse to that sphere. And so in between here, you have this coordinate sort of space between Y and S3. So what is sort of enabling this picture is that B4 is convex. So you get this Liouville field at the X3 end. You have W being symplectically convex means that B4 minus W, this is what you would call a strong symplectic abordism. By which I mean a smooth cobordism with a symplectic structure and having Liouville fields kind of pointing in at one end and out at the other. And sort of the key thing that's necessary for us is that the reduced Floer homology of S3 is 0. It's kind of the first calculation you do in Heegaard Floer theory, I guess. The theorem becomes a consequence of the fact that a strong symplectic cobordism, well, Heegaard Floer is some kind of TQFT to, cobordisms are supposed to give you homomorphisms in the corresponding Floer groups. A strong symplectic cobordism, it turns out, the induced homomorphism behaves nicely with respect to this contact class. And well, technically, since it's a cohomology class, they map backwards. So what that's telling you is, at least morally speaking, the contact class here is the image of the contact class from S3. Contact class from S3 satisfies the conclusion of the theorem because of this property. And then the naturality gives it to you for the one you're starting on. If you're kind of keeping score, that naturality behavior of these maps under strong symplectic cobordisms isn't quite as established as I was just suggesting in the case of Heegaard Floer, where it is established. Is in the monopole Floer setting. So there's a theorem of Mariano Echeverria, that saying. And then, well, even though so monopole Floer homology is sort of Cyber-Witten Floer homology, if you like, and Heegaard Floer homology are known to be isomorphic for 3-manifolds. It's not quite known that the maps induced by cobordisms correspond, but the algebraic condition that we need at the end, namely the vanishing of this, if you can prove that in monopole, then that correspondence at the 3-dimensional level is going to be the same thing. So that correspondence is due to Kutlo, Hadley, and Taubes, together with the very different version of Kolan, Gajini, and Honda. So maybe I'll write all those names up. Okay, so that's the obstruction. So if you want to show that something is not contact type hypersurface on R4, it would suffice to show that this invariant of some corresponding contact structure doesn't vanish. Of course, this is an invariant for one contact structure at a time, and I said we weren't supposed to fix that ahead of time. So you want to sort of show that property for all contact structures on the 3-manifold. And if you're looking at a Brieskorn sphere in particular, there's sort of a annoying complication, which is that there's not, in general, there's not a classification of the contact structures on Brieskorn spheres. In many cases, they're classified, but in general, we don't know. So that's sort of where the heart of a large piece of the work is. Proving the theorem. That's the part that I'm not going to get into. I'm just going to sort of tell you that obstruction is enough to get what we want for Brieskorn sphere. The theorem is if you have a fillable contact structure on what I'm going to call a suitable Brieskorn sphere, then this reduced contact class is for 0. Okay, and so that if you believe it, well, modulo the word suitable, that'll tell you this here. Okay, so what does suitable mean? Well, I don't know, maybe it's not super important. let's just say it out loud for the moment, unless there are questions. So a Brieskorn sphere, right, it's a link of a singularity. So that means like that singularity, you can resolve it by blowing up, right? You have a minimal, say a minimal good resolution will be some sort of plumbing of two spheres in this case, that topologically, the exceptional set for that is some graph of two spheres. And so in other words, that Brieskorn sphere, if you think of it as the boundary of that resolution, that's the boundary of some plumbed 4-manifold. And so this suitability condition is that the intersection form of that 4-manifold be diagonalizable over the integers, which is a necessary condition to even embed smoothly in R4 by Donaldson's theorem. So this isn't just doesn't affect the applicability to the case at hand. But okay, leave it at that for now. Okay, so let's think about when did I start? 12:30. Let's think about other 4-manifolds. So the thing to bear in mind, if you want to do this generalization, in particular, I'm interested in closed symplectic 4-manifolds. Essentially, I want to try to generalize this obstruction. So, if I have some symplectic 4-manifold, maybe a closed one, I want to try to produce some sort of obstruction like this to a 3-manifold, maybe a contact 3-manifold, arising in there as a contact type hypersurface. And if you think about it, well, there's various ways you might think about it. You are sort of led before very long to the following. So here's theorem 2. Say you have symplectically convex domain inside some symplectic 4-manifold. So its boundary is some contact 3-manifold like C. And the assumptions I will need, I mean, the thing is that anytime you have a fillable contact structure, it sits as a contact type hypersurface in some symplectic 4-manifold. You can just construct such a thing. It's not like you're going to say that Y never appears as some contact type hypersurface. So you're going to have to, it's really constraints on X that are going to be necessary. So let's assume there is some symplectic curve curve, but I mean real two-dimensional surface, and a sigma in the complement. With the following properties, it should have positive self-intersection. And it should have positive Chern number. Okay, so then under those conditions, you get the same conclusion as over the reduced contact class, but its contact structure should vanish. And the analog with the properties over here is the following. I mean, if you like, you should think of this picture. This is a picture in C2, but think of C2 as the complement of a line in CP2. So the line is sort of, the role of the line is played by sigma over there. But in general, you have a picture something like this. Here's your Y, there's your W. You're assuming that there's some curve out here, sigma. And the conditions you need are, well, it's, S3 was convex. And to put it another way, the line in CP2 has a concave neighborhood. And that, symplectically, that what you need for that is this positive self-intersection. So this is giving you, well. So that's telling you that the space from Y to the neighborhood of sigma is a strong coordism. And the Chern number condition, so that's this bullet point. The Chern number condition is essentially the analog of this. It says, so this is the first condition, and then this Chern number thing. That's the same by the adjunction formula. You have a symplectic curve. That's the same as saying that the self-intersection actually is bigger than 2t minus 2. And again, there's sort of an explicit calculation of what the Floer homology of the boundary of a neighborhood looks like. And in this circumstance, you have no reduced Floer homology. So then you get the conclusion follows for the same reason as before. It's sort of this naturality business based on Ashbery. Okay, so that's a generalization of the obstruction, but the question becomes, when can you ever kind of ensure that this applies, right? If you're kind of, for what X can you arrange that anytime you find a symplectically convex domain, you can always get these curves in the complement with these conditions. Well, with that in mind, you'll just state a result. And then I'll try to say afterwards why, how you see that this theorem gives you the consequence. So here's sort of here's sort of a sample application, I guess. So let's suppose you have a Heegaard surface and projective surface. With the first Chern class pairing positively with this homology class of the symplectic form. I guess I just mean the product integrated over X. So for example, you might have a rational surface. This is a pretty constraining condition if you sort of understand how classification of complex surfaces goes. This is sort of saying that you have cotard dimension minus infinity, basically. So there's not that many of these things, but there are some. So a rational surface, say, diffeomorphic to either S2 plus S2 or S2 along with some number of points, but more than 9. Then if you have a contact 3 manifold and it has this reduced class non-zero, then claim is that it doesn't admit any embedding as the boundary of a, well, goes to symplectic embedded. Rationally convex domain. So the way you're supposed to read this is that all the hypotheses and constraints I put on there are sort of there to make sure that these hypotheses are in place for the obstruction to apply. In other words, if you have positive turn number and you bound something rationally convex, then there should be a curve in the complement with these properties. That's sort of what's going on. So the rationally convex part is basically the assumption that there is such a curve. So I think I erased the definition of rational convexity in C2, but it's more or less the same definition in a projective surface. Namely, it should be rationally convex if and only if for all p in the complement, there's some algebraic curve, sigma, also in the complement containing p. So as a corollary, at least if you buy this theorem, you get, because what we know about the contact invariance for contact structures of Brieskorn spheres, no suitable Brieskorn sphere bounds a rational convex domain in a rational surface with, let's say, E2 no more than 10.
Sorry, can you explain again, where is this condition coming from, like the limit on B2?
It's because that's the situation in which you know that every Kähler form, even every symplectic form, satisfies this condition. Once you go past 9 blow-ups, there are examples of what some people call negative symplectic structures, or trend pairing negative.
And here you have to keep this suitable because you don't know that there's.
That's right. So an example of one that's not suitable is the Poincare sphere. And that one does bound a rationally convex domain in the rational elliptic surface. That's the case with K. On the other hand, the suitability is sort of the invariant we have about the contact class should have this certain property certainly doesn't capture everything. And like in the case of C2, like there are examples where Nemirovsky-Siegel, for example, showed certain domains are not rationally convex. They don't have contact type boundary that our obstruction doesn't apply to. So in that you shouldn't sort of get the impression that this obstruction is supposed to capture everything necessary. But, at least in this situation, there is some degree of sharpness in some sense. Okay, I'm not going to go much further here since we're at the end of the time, more or less, but maybe I'll just state the result that sort of ties things together here. Like we're back talking about rational convexity, whereas before I was trying to talk about contact type, and this rational convexity was this funny business that we had before. Well, existence of curves, you can maybe see how that needs to come in, but it's sort of it's not exactly a symplectic condition on its face. So the theorem that sort of puts things together is relatively new, I guess, from last fall by Boudreau, Gupta, Shafikov. It says that a Stein domain, say W, in one of these algebraic surfaces, that's rationally convex. If and only if this, so it's sort of analogous to condition 3 that we had at that theorem before, that, so it's Kähler form. Omega phi coming from the Stein structure of W extends to all of X as an integral Kähler form. Moreover, so remember, rational convexity is about existence of these algebraic curves in the complement. So they didn't state this in their theorem, but it's part of the proof.
Biologist, physicist.
In this case, curves you find can actually be taken to be, that's what you would think of as like Lefschetz divisors or something. They're Poincare dual to the a multiple of that.
Sam told me the same thing at the Harvard Society. When he interviewed the.
Let's get it from X. Okay, so then, right, once, if you have this condition, then they certainly have positive self-intersection, and the Chern number condition translates into this Chern number condition once, if sigma is just a multiple of symplectic form. So that's sort of how these sort of fit together. And well, that plus what I was saying when you go, so as far as the corollary, this positivity is sort of known to hold into this situation for any Kähler form, but in general, you have to be more careful. So I guess that's more or less the story I wanted to tell you. You know, if there are questions, I could say a little more.
Any questions?
So does the contact class can have some components in the non-reduced part? And is this from issue relevant or?
Well, I mean, if you're being careful, like that decomposition I wrote as the non-reduced plus the reduced, that's not really a canonical. It's really just a short exact sequence. So it's either sort of in the non-reduced part or it isn't. So.
Do you think these Brieskorn spheres could be like convex type hypersurfaces in higher dimensions?
In higher dimensions? I imagine so. I mean, like I said, in higher dimensions, there's this Chilliback affiliation work that says that basically as soon as you bound a Stein domain in CN, you're rationally convex for contact type in CN. And I haven't investigated, but I would imagine that you could find some Brieskorn spheres that do that. Yeah.
And in dimension 4, do you know what happens if, like, do you have any examples for K larger than 9? Like with this Stein number condition violated basically?
Yes. So, so I mentioned, well, not what you were asking, but I mentioned Poincare spheres. So that's sigma 2, 3, 5.
Yeah.
This one is rationally convex in E1, so CP2 blown up 9 times. But it turns out that if you just go to sigma 2, 3, 7, this guy is, there is a symplectic structure on the tenfold blow up. for which this guy is a contact type hypersurface. It's not clear whether the symplectic structure you get is a Kähler structure. And so like, should I call that rationally convex or not? That's not really clear to me. It's sort of stuff we're trying to work out. But at least there's a symplectic structure here where that's contact type. So that one of the kind of things we're trying to think about is how to sort of divorce the complex analysis from the symplectic geometry. This is a little bit of a hybrid. So we'd like to have sort of a more symplectic, well, maybe not a symplectic version of that theorem, but sort of more purely symplectic version here that's talking just about symplectic convexity instead of this rational convexity stuff. So that's in progress. But in any case, this guy is contact type in 10 blowups. You could conjecture that there's no symplectic structure smaller where it would be contact on a smaller blowup where it would be contact type, but it is pseudo-convex in CP2 blown up once. So in other words, it bounds a Stein domain in there, but not something rationally convex, and presumably not anything opposite.
If you replace 7 with other primes, like just keep increasing p, do you still know that it embeds as a symplectically convex thing in some bigger blowup?
Yeah, I think you can do a lot of this in pretty good generality. We haven't tried to write down formulas. It's a pretty general construction. This is, the family here is 2, 3, 6n plus 1 that this would fit into, so you can pretty naturally do both of these things. This, like if you increase n, then you might have to make this bigger, but actually sitting here, you change the complex structure, but it's still the same.
Any more questions? No, let's thank Tom again.